So we can use the form of an exponential function to tell some things about the pattern, just like we could for a slope-intercept equation. So the slope-intercept equation, remember the slope was right in there. That was at m and mx plus b. That was the rate of change. And so was the y-intercept. So that was usually some kind of a starting value. That was the b in y equals mx plus b. So in exponential form, we have the same thing. So in exponential form, we know that this starting number, often called a, that is our y-intercept. That's our starting value. So if that is our starting value, then that means that the starting population would be 15 rabbits. And that's the starting number because when n is 0, if you use your calculator and put in 15 times 1.2 to the 0 power, so after no time has passed since data was being collected, you will get 15. That's because any number to the 0 power is 1, which seems weird. So 1.2 to the 0 power is equal to 1. 15 times 1 is 15. We'll in our next unit of new learning next week, we'll learn a little bit about why that is. But for now, deal with it. And then the other thing that we know from the exponential equation is that this is our growth factor is 1.2. That's our multiplier. So when we predict the population, we're doing 15 times 1.2 times 1.2 times 1.2 and so on. So there's our growth factor of 1.2. So if we want to see after how many years the population is going to double, there isn't really a shortcut, like I said. So doubling would mean the population goes to 30, but there isn't really a shortcut for this. Like I said, so you can think of a table where you have the number of years and the population, and it starts at 0 years, you have a population of 15. And if you repeatedly multiply 15 by 1.2, 1.2, you'll see it grow. And you're just seeing how many times do you need to do that in order for the population to get up to 30. So jump to your calculator. 15 times 1.2. There's once, twice, 3 times, and at 4 times it goes just beyond double. So we're not going to worry about decimals with our number of years. We're just going to say that at 4 years, the population has doubled to about 30 rabbits. So somewhere between 3 and 4 years, but definitely closer to 4 years. So going back, we want to see what the population will be after 3 years and see how long that would take to double. This doubling period is kind of an important concept because it's not intuitive when we're used to linear change. So if we go back, we can see that at 3 years, it was at, right here, 25.92. Let's just round that to 26. So after 3 years, we've got 26 rabbits. That's 15 times 1.2 to the 3rd power. And we want to see how many more years will it take for that to double. So doubling means it's going to go up to about 52 rabbits. And it's okay to kind of fudge these numbers. Don't worry about those exact decimals. So we're going to double it. So going back to the calculator, we can see how long it takes to get to 52 years. So if right here we were at 4, I could do 5, 6, 7, for about 7 years at that point. That's about 7 years. Then we're going to do this one more time with the population at 10 years. So after 10 years, that's 15 times 1.2 to the 10th power. See, if this was 7, I can just go 8, 9, 10. We're at about, let's say, 93 rabbits. And if that's going to double, we're looking for it to be at 186 rabbits. So I'm going to pause here, and you might think that as a population gets bigger, it takes a longer time for that population to double. But notice the first time we looked at it, for the first time for it to double from 15 to 30, that was 3 or 4 years. Notice it's kind of a number about another 3 or 4 years for it to double from 26 to 52. Also, seems like it would take longer to double 93 rabbits to 186. But if you look in your calculator, I'm going to go 1, 2, 3, 4. It's another 3 or 4 years. Another 3 or 4 years to double, just like this one up here. That was 3 or 4 more years. So notice that counterintuitive part is that 3 or 4 years stays constant. It takes the same amount of time for the population to double no matter where you're looking at in the pattern. And that's because as we're taking our 15 times 1.2 times 1.2 times 1.2 times 1.2, 1.2 to the fourth power is about 2. And so if we keep going, times 1.2 times 1.2 times 1.2 times 1.2 times 1.2, if we keep going, it doesn't matter what set of 4 times we multiply the population by 1.2. 1.2 to the fourth power is always about 2. So if you take the population at any point at this rate, it's always going to take about 3 or 4 years for it to double, because it doesn't matter which string of these you look at. Multiplying something by 1.2 4 times is the same as multiplying it by 2. So it doesn't matter if it's the first 4 years or if it's from the second year to the 6th year or whatever, it's going to take the same amount of time for it to double no matter what. That's because even though the number's getting bigger, it seems like it would take longer to double. Remember, with exponential change, your graph looks like this. So even as the population gets bigger and it seems like it would take longer to double, notice the slope is getting steeper as time goes on. So those two things kind of offset. So if you look at like each of these phases, it's a bigger number to double each time, but it's growing faster, so it kind of, those two things balance out and it takes the same amount of time for the population to double. So same doubling period at each interval. And that's a characteristic of exponential change. So for this last problem, when we actually report growth, we tend to use percents. And this is kind of a bridge to the next extension option, is going between growth factors and what are called growth rates, which are percents. And so for this one, if you are, like for the first one, if you multiply something times 1.8, you'll notice the number goes up by 80%. At 80%, that's that 0.8, 80%. So like for that first part, if the population goes from 100 to 180, that population, it goes from 100 to 180, that's an increase of 80 rabbits out of 100, 80 out of 100, 0.8, also known as 80%, which is what you tend to see reported in articles, the news, any kind of statistics, whether it's scientific stuff like this or if it was sports, they tend to use percents. instead of whatever the multiplier is to achieve that percent change. So for the other one, that means if you're multiplying something by 1.2, that would be a 20% increase. So again, if let's say we had that 100 wraps at the beginning of this one, because 100 is what percents refer to, you went from 100, multiply that by 1.2, you'd get 120. That's 20 more rabbits. 20 out of 100, 0.2 or 20%. And there will be more on that in the next extension activity if you decide to do that.